My net goal is to do calculus. We started with limits. What follows? Derivatives and integrals. So this basic idea is exactly the same. If I have some vector valued function, R of t, how do I take its derivative? I need to make the white balance different. There. Now it'll show up better. Well, I'll do the same definition we've done before. I'll say, okay, R prime of t, or dr dt, is going to be the limit as t goes to 0, sorry, as h goes to 0, of r of t plus h minus r of t over h. That's the exact same limit definition we used in Calc 1. So frickin' what? Well, R of t is a component-wise function. So if I'm doing this subtraction right here is subtracting two vectors. How do you subtract two vectors? So this is really the component difference, right? But what we did on Monday tells me that when I take the limit of a vector, I really just take the limit of the components. So instead of having one limit outside, I have three limits inside. Which means that in each individual component, the limit expression we've written here is exactly the definition of derivative from Calc 1. And that means that this is just x prime of t, y prime of t, z prime of t. In other words, taking the derivative of a vector is taking the derivative of the components. It's just like Calc 1, except I have to do three of them instead of one of them. Like Calc 1 with more variables. That's it. I said it like 5 different times. It's the same damn thing. Great. That's beautiful. That's wonderful. It means I know how to do this easily. Okay. Here's a familiar looking curve in three-dimensional space. What curve is that? That's my helix going up. Okay. I don't just want the derivative arbitrarily. I want a specific point, right? When we did derivatives, we would plug in a value. Prime of t at the point -1, 0, pi. Now, this is slightly different than when we did derivatives in one variable. Because when I did derivatives in one variable, I wanted f prime of x at a particular point, I wrote f prime of 2. I wanted f prime at the point a, b. Well, if it was x, y, well, then all I had to do was plug in the x. But these are parametric. So I need a t value. They gave me a point. How do I get the t value? The last component says t equals pi, doesn't it? Does that work? What's cosine of pi? And sine of pi is 0. That is the right value. Okay. Yes, I matched these up, but then I'm fortunate enough to know that t equals pi. So now you can actually give me the value of this derivative. What's r prime of t as a function? Exactly. All I have to do is take the corresponding derivatives of each of the component functions. And so I can do r prime of pi, plug pi into those, and you get 0. That's what happened when I plug in pi up here.
Oh, sorry. It's the 0, 1, 5, sorry.
Look carefully. You sure about that? I still think there's something wrong there. Sine of pi is 0. Cosine of pi is?
Oh, cosine of pi is -1. Sorry.
It's okay.
Yeah.
It's always the little mistakes that are going to put me up. Okay, wait a second. I need some help understanding what this means. When we did derivatives in Calc 1 and we got the derivative at a point, what did that represent? The slope of what? I don't know how to take the slope of a curve. We only know how to take slopes of tangent line. So I should have a line, right? Okay, I'm going to be a crappy artist again, but let me draw my helix. These marks are all 1 unit out. So I have 1 in the x, 1 in the y, 1, 2, 3 in the z. So far, so good? Now the helix starts at 1, 0, 0. When t is 0, when t is 0, we're here. And then I go around the circle counterclockwise, but I also go up. Yes? So I am standing at the origin. I am pointing at the point 1, 0, 0. T starts to advance, and I do this. When t is pi, I am at the point -1, 0, pi. So my helix ends at a point up here like that. That's going around and back. And then it keeps going, and it starts to come around and come around the front again, right? But here is the point r of pi. Like that. Jan, I can only take the slope of a tangent line. Where's the line? I didn't create a line. I don't have the equation for a line up here, right? We would get the derivative, and then we'd say, okay, then the equation of my tangent line is, and we would do all that crap. I didn't do that yet. But I would, on the graph, normally I would draw a line that just touched in one point, right? I want to draw that line here. That line has to go through that dot there. And it has to have this slope. Okay, wait a minute. That means it doesn't go in the x direction. It goes in the negative y direction, and it goes up. And since that is -1 and 1, that's a slope of 45 degrees, right? So there should be a line back here that goes up and to the left. -y, positive z. Should go that way. Now, I will agree with you that at the moment, this is kind of weird looking. I did this automatically without thinking about it as a 3D image. Let me do a 2D one as well, but before I do that, I want to do one other thing. I didn't get the equation for a line. But we know how to do the equation for a line when we have a slope and a point, right? I have this slope, I have this point. Well, then the equation for my tangent line should look like the equation for a line, shouldn't it? So the tangent line through this point with this slope should be this. This is the equation of my tangent line. And if you would like, you are welcome to write that in parametric form rather than in vector form. So you could also write x of t equals -1 plus nothing. Y of t equals 0 plus -t. And z of t equals pi plus 1t. The difficulty is seeing it, and unfortunately I didn't bring my junk with me, but if my helix were on this cylinder, the front would be facing you from my orientation, like it is on the board there, and we would go around to the back of the cylinder, and we would be going up behind the cylinder. A two-dimensional example. Let's just do the circle. So my R of t here is cosine t sine t. Now, I can either give you a point and ask you to figure out the t value, or I can give you the t value. But me already told me how to figure out the t value from the point, so it works either way, right? What t value goes with that? Exactly. So, before I do anything else, there's a vector pointing at that spot. That's r of pi over 6. What's r prime of pi over 6? Well, let's do r prime of t first. And we get and that means that r prime of pi over 6 is negative root 3 over 2. No, I can do my trig functions, really. Negative 1/2 root 3 over 2. What direction does that point? So it's pointing towards the second quadrant, yes? Again, I'll change colors just so we can see it differently. We should be going this way. And notice, in addition, I've drawn this time, I've drawn the origin, the tail of this vector at the point in question. Kind of like it's actually a physical dot. And I said, okay, the vector is going to be coming out of that dot. I could put it in standard position, but I chose to put it at the point on the curve because it's the slope at that point. Yes, maybe, no, kind of. Again, you could find me the tangent line. You know the slope, you know the point. You could come up with this set of equations again here in 2D. Questions? It's a lot easier to picture, I think, flat. But I think that just might be me. Talk to me, people. Either that or I'm going to assume that lunch has you all in a coma.
The helix,
Yes.
I don't understand why the direction of the tangent line.
So let's go back to the calculation we did there. Right? There's my r prime. Now, remember, my helix started in front of me. Wait a minute. Watch my thumb. I'm going that way. I'm going left and up as I keep climbing. It's a circular staircase. Which way am I pointing as I go up the stairs? Oh, by the time I've gotten to this spot on the stairs, I'm going that way.
So it's, yeah,
In one sense, it's the direction vector. In another sense, it's the vector I am going, right? Wait a minute. I can get the physics application here. If it was position, the derivative position is velocity. Speed is a scalar. Well, velocity is a vector. So it's a vector. That's my velocity. If I was pulling this movement, I would be going up, and at that spot, I'd be going up and left. This particular pair of tangent vectors, one of them is significantly more useful to me than the other one. I like this one better than this one. And I promise that's not for what is a completely arbitrary reason. What's the length of this vector? What's the length of this vector? Square root of 2. So it's useful to me sometimes to not just have a tangent vector, but to have a unit tangent vector. I'm going to call that capital T of T. And we always find a unit vector by taking the vector we want and dividing by its length. So in our case, in the second Yano, what's not clear? My handwriting sucks, I know. A unit, the bad U. Unit tangent vector. So in the helix, we were at the point where t equals pi. So I would divide by the square root of 2. The second one was the -1. There we go. And on the circle, sorry, t of, not t prime. Get rid of that. Just t of. Sorry. There's not a prime on this part. There's prime on the r, but not on the t. T of pi over 6 equals r prime of pi over 6, since length of r prime of pi over 6 was already 1. Now again, I am a horrible artist. So here's a different spot on our helix. On page 857, example 3, they did pi over 2 instead of pi. So here's the helix. And at pi over 2, we've gone a quarter of the way around the circle, and we're going back and up. We've only gone a quarter of the way around the circle. We're pointed to the behind. Here's another one in 2 dimensions. Page 857. Reason we use unit vectors more often is because it dissociates the direction we're going from the speed, right? I just want to know which way we're going. Let's use a unit vector for that. I don't care how big or how small it is, just that way. questions? We will take these unit vector ideas further. There are some benefits to the way we do unit vectors and what comes of them. So that T is going to come back to us. Well, if I can do it once, I can do it again. Go back to our helix. Our derivative, r prime of t, right? That means I can do r double prime of t. What do you get for r double prime of t? Derivative constant is? Okay, wait a second. What happens when I plug pi into that? One, zero, zero. I don't like when it's wrong, Mia. She's like, it's okay, it's okay. Okay, wait a minute. What direction does that vector point? 1, 0, 0. I got to go back to my picture. My picture of the helix. We're at this spot. Our velocity is this way. That's our tangent line. This second derivative is pointed straight back at you. In parallel with the x-axis. Now, those of you with a slight physics bent, I have a piece of vector pointed in towards the center. What do we call that? Centripetal force. I'm going in a circle. I have centripetal force. Force is mass times acceleration. That must be an acceleration vector. It works in 2D also, by the way. Doesn't matter whether it's in 2D or 3D. First derivative, second derivative. I can do as many derivatives as I want. When we were doing curves in 2 dimensions, we had tangent lines that were horizontal when our derivative was 0, tangent lines that were vertical when our derivative was undefined. But because I have a vector here, I can point in all those different directions when my derivative just gives me a value, right? I always have a direction when I have a vector. Wait, that statement is false. What vector has no direction? The 0 vector. So if my derivative is 0, not just 0 in one spot, but all 0 anywhere, then I have a problem. So I'm going to say that my function r of t, if you're messing with me, I'll use something else. R of t is smooth if r prime of t is not equal to 0 for any t in the domain. And R prime of t is continuous. So I want continuous, non-zero derivatives. Now I'll make an exception at an end. If I only have like a closed interval for my domain, then maybe at the very starting point, you could have your derivative be zero. Maybe at your very end point, you could have your derivative be zero. I'm okay, except maybe at the ends. Any t in the domain, except ends. Now let's think about this for a minute. I would like you to do me a favor. Let's take a look at a graph. Parametric equations. I can draw parametric equations. X of t equals 1 plus t to the third. And y of t equals t squared. And this time, I'm going to set the range of t's to go, say, -3 to 3. I don't need a big range, but I want to look at what happens. Oh, so I have -4 to 4 in here already. Let's just leave it like that. When I graph this, oh, I wonder what t value that is. What's r prime of t? That is 0 when t is 0, right? Guess what? That spot, that's where t is 0. And my curve isn't smooth there. It's got a point, a cusp. And if I rewrote this equation in y and x, if I eliminated the parameter like we did back in chapter 10, I could actually see that my regular ordinary derivative would be undefined there. Because from this side, I have a tangent line that should be vertical. And that means the slope should be -infinity. But if I come from this side, the slope should be positive infinity. We have a problem. So the definition of smooth replaces the idea of being not differentiable in 3 dimensions. Questions? Sneaky booger did exactly what I wanted it to do. Yay. So this is a curve that is not smooth at 0. It's smooth everywhere else. It's not smooth at 0. My favorite part about taking derivatives like this is that all the same derivatives will still work. Page 858. The derivative of a sum is the sum of the derivatives. The derivative of a constant multiple, pull the constant out, take the derivative the same way. The derivative, oh, wait a minute, what the hell's going on here? 3, 4, and 5. 3, 4, and 5 are all product rules. But we have different options for products. Remember, you can multiply a vector by a number, right? So in this case, I'm multiplying the vector u by some regular function. So that's a multiplication. You take the derivative of the function, leave the vector alone, take the derivative of the vector, leave the function alone. Here I'm doing a dot product. Derivative of the first times the second, or the second times the first. Here I'm doing the cross product. Derivative of the first times the second, or the second times the first. It's the same product rule. It just depends on which product we're using. A regular product, a dot product, or a cross product. It's the same product rule. And the chain rule works the same way too. And since I'm just doing the same derivatives, this is a godsend. Product rule, quotient rule, they all work the same way within the functions. I don't really divide vectors, so I'm not worried about u over v. But it works exactly the same way. Questions? Here's an interesting example in the textbook. Why I'm not putting the book down yet. Down here at the bottom, example 4. It's just one sentence up here. It says, show that if the length of R is a constant, then R prime is perpendicular to R. Always. Why would that be true? If the length of R is a constant, if the length of R is a constant, then I also know that the length squared is a constant. That's not hard, just square both sides, right? But by definition, the length of a vector squared is the dot product of that vector with itself. So I now have R dot R equals a constant. Ready for the sneaky part? I want you to take the derivative of that line. What's the derivative of the right-hand side here? Oh, C is a constant. It's the derivative of a constant. 0. So when I take the derivative, I know on this side I get 0. But on the left side, I do the product rule. So I get the derivative of the first times the second plus, leave the first alone, do the derivative of the second. So far, so good? Wait a minute. This is a dot product, right? Does the order matter in the dot product? I know the order matters in the cross product. Does the order matter in the dot product? A dot B versus B dot A. Chapter 12, section 3. Turn back and take a look. In the cross product, we got a vector, so the order changed which direction we were going. In the dot product, we get a number, and it turns out not to matter. Page 807. So that means that R dot R prime and R prime dot R are the same thing. So this left-hand side is 2 R prime dot R. Because it's one of them was written with the R prime on the left, the other one was written with the R prime on the right. I'm going to divide by 2, and I get R prime dot R equals 0. Why does that make me happy? I'm a sick mother. No, there's a reason there. Unfortunately, no. If the dot product of two things is 0, two vectors. The dot product of two vectors is 0. They're perpendicular to each other. Because of the cosine thing, right? I don't have to have one of them being 0. Matter of fact, I know r length of r is a constant. Then that's not a 0 number, I hope. But then these must be perpendicular. And that means that the derivative is perpendicular to where the line pointing where. Wait a minute. Let me go back to those pictures again. I'm a crappy artist, but take a look at this. There's the vector pointing at the point. There's r prime. The angle between them is 90 damn degrees. There's r prime. The angle between them is 90 degrees. I'm pointed at this spot on the helix, and my curve is going this way, and the angle between those two is 90 degrees. Son of a. And so literally, I cheated when I did it. When I made the picture of the helix in my mind with all of you, I stuck my arm out and I said, watch my thumb. My thumb is at 90 degrees to my arm, isn't it? I did it deliberately and none of you caught it. That's why, because I'm going around at a constant speed. If your speed varies, this changes. This is only guaranteed to be true when your speed is a constant. And that's what we talk about with tangential and centripetal acceleration back in physics 1. Okay, I had to do that. I am a former physics major. This is where this really starts to get, oh, wait a minute, these go together for a reason. Whew. Questions? I have spent 43 minutes doing derivatives. And the title of this section was derivatives and integrals. Where are the integrals? If I want to do a definite integral of a vector function is the definite integral of each of the component parts. I just have to do the same thing, but 3 times instead of 1. Which means I can also think of the fundamental theorem of calculus. You could take an antiderivative, but an antiderivative of a vector, I'll do an easy one. R of t equals t squared, t cubed. We'll just do this, the twisted cubic. If I were to integrate this with no numbers, then every time I do a definite integral, what should I end up with? Sorry, every time I do an indefinite integral. What do I end up with after I do an indefinite integral? At the end of every indefinite integral, what do we write down? Plus c, right? I got to write down a plus c. But I'm going to have to write down a plus c for the x, and a plus c for the y, and a plus c for the z, which means I have 3 of them, which means I have a vector of c's. See how I got a constant that goes with the x part, and a constant that goes with the y part, and a constant that goes with the z part? means I end up with another vector plus c. Now, one big issue. I'm not even going to make up the problem. I'm just going to steal it right from the textbook. I hope it's still the same problem. I have to write the problem from the old version of the textbook. This used to be problem number 35. Problem number 35 went like this. Now, I will say that this particular R of t draws a very interesting looking thing in 3D. It does. It's very pretty. If you graph this, you'll get a nice picture. I think you need to go from 0 to 4 pi to see everything clearly. I'm not 100% sure I recall that correctly, but at least 0 to 2 pi. But in order for me to solve this problem, I have to integrate this. Then I have to integrate this. Then we did all of this in chapter 7 back in Cal 2, and these were all the crazy integral things we ran into, right? Oh, crap. That was trig integrals, and then we had trig substitutions, and we had partial fraction. I'm going to have 3 times as many integrals. That means I increase the likelihood that I will run into an integral that sucks. I am going to rig problems as often as possible. And I will tell you right now that all 3 of these are rigged. These are simple u substitutions, all of them. Here, the derivative sign is cosine. So this is 3u squared du. Here, the derivative cosine is minus sign, so this is 3u squared with a minus sign du. And this, the derivative sign is cosine, so this is 2u du. We know how to do these. It's been a while. So I better crank up my ability to do integrals. But it should all still be in here, I hope. Write that down, I hope. Please go back and review the integral techniques in chapter 7, the same ones that we used in chapter 10. We're going to see them over and over and over. That means that the applications that showed up in chapter 8, we'll see those as well. But that means the integral problems in and of themselves are no harder than they were last year or whenever you took Calc 2. Yay. Again, I will rig problems as often as possible, but in this case, I'm going to have to do the appropriate u substitution in each case. And then once I do the antiderivative, I'll have to plug in 0, plug in pi over 2, and I'll get a number. By the way, if I wrote it out correctly, the correct answer to this problem is 111. So with a little bit of work, I think that's the answer. But you won't see this until the second exam, because The exam for Monday ended Monday. Normally, the exam would be tomorrow, but we don't have class tomorrow. Because I've got that math competition thing going on. I will have office hours, I hope, because they said they expect to be done at 1, and my office hours start at 2. So I should have office hours tomorrow. If you've got questions, come bug me. I will see you all Monday. I hope you have a wonderful weekend, because I won't see you tomorrow. Unless you come to the math competition.